So I'd like to tell you about this piece of work on a quantum algorithm for nonlinear dynamics. And this is joint work with my PhD student, Jin-Peng, who's actually speaking later on in this meeting, together with our co-authors, Herman, Nuno, Hari, and Konstantina. And there's a paper that you can find on the archive that talks about all of the work that I'm going to describe in much more detail. Okay, so this is, I guess, the first talk of the meeting. So let me sort of start with some, very basic sort of background that's probably familiar to many of you. So, as you know, we're interested in understanding what are the things we can do with quantum computers that we can do faster than we could using classical computers. And as I'm sure you're aware, there are different kinds of speedups that we can hope to get from quantum algorithms, which include, for some problems, we think exponential or super polynomial speedups. These include problems like, factoring, but also things like simulating quantum mechanics, which is maybe a bit closer to the kinds of things we're going to be interested in during this meeting, and also, other various kinds of problems. And there are also a variety of problems, I would say a wider variety of problems for which we think we can get polynomial quantum speedup, so less than exponential quantum speedup, but still a potentially significant improvement. And the sort of variety of problems for which we can get such improvements is perhaps larger. So in this talk, I want to talk about, specifically about, tasks related to high-dimensional linear algebra. And so this is sort of an area that I think has seen a lot of, recent interest. The goal with a lot of these problems, including the ones that I'm going to talk about today, is really to get exponential quantum speedup. But this class of algorithms kind of approaches the problem in a rather different way than we see in, for example, the factoring algorithm. So the idea of these algorithms for problems in high-dimensional linear algebra, at least the ones that I'm going to talk about, the basic idea is to represent the vector that is the solution of the problem you would like to find by a quantum state proportional to the to this vector. Was there a question? I saw a hand go up briefly, but please do feel free to ask questions during the talk if you have them. I'm happy to take them. And then our goal is to prepare that state efficiently, right? So this is an n-dimensional quantum state, but you can represent it using a number of qubits that's only logarithmic in the dimension of the state. And we would like to actually prepare that quantum state also using a number of gates, which is only polynomial in the number of qubits, not the dimension, but polynomial in the number of qubits. So that's sort of exponentially better than you would be able to do if somehow you had to explicitly represent the vector. Now, since we were only producing a quantum encoding that gives some kind of implicit representation of the solution, it's definitely not the same thing as having an explicit solution, right? It's less informative to just have this quantum state than to actually have written down an entire vector that represents the solution. But on the other hand, this is something that we can do a lot faster, and it's still potentially useful for some kinds of things. So this is going to be our goal, is to think about this sort of version of solving a linear algebra problem by representing the vector in a quantum state, and see how fast we can do that, specifically for problems having to do with nonlinear dynamics. Okay, so this idea of representing the solution in a quantum state is somehow very natural in the context of quantum simulation, which really was like the thing that led to the idea of quantum computing in the first place, right? So you've probably seen this quote from Feynman where he sort of observes that it would be very natural to build quantum computers if the problem we would like to solve is simulating quantum mechanics. And so in the kind of the quantum simulation problem, the problem of simulating the dynamics of closed quantum systems, we're given some kind of description of the Hamiltonian of a quantum system. We have some time we want to evolve for. We have a copy of the initial state, and our goal is to produce a copy of the final state in the memory of our quantum computer. And it's usually okay to do that up to some approximation. Now, this is a task, as I've described it, that is not even one that we can pose to a classical computer, because the input is a quantum state written in the memory of a quantum computer, right? That's not something we could hope to explicitly represent classically. Then again, a quantum computer is not producing an explicit description of the solution. It's producing a copy of the quantum state. So we really can't make a sort of apples to apples comparison between classical and quantum approaches to this question. But if you would think about initial states that you can efficiently prepare from a succinct description, and then think about performing measurements on that quantum state to produce classical data, from the statistics of the measurements on the quantum state, then you could phrase the problem in a way that's sort of classical in the input and classical in the output. So it's something you could in principle pose to a classical computer. And when you describe the problem in that way, you get a problem that is apparently hard for a classical computer. In particular, it's as hard as anything that a quantum computer can efficiently do. So if you believe that factoring is a classically hard problem, or indeed if you believe that there's anything that classical computers can do that quantum computers cannot, then quantum computers get an advantage for this kind of problem. And this idea, this kind of ability to simulate Hamiltonian dynamics efficiently, is really kind of at the core of many of these algorithms for quantum linear algebra, including the ones that that I'm going to talk about in a bit. Okay, so the kind of obvious way to use quantum simulation is to do computational quantum physics, right? To simulate chemistry or condensed matter systems or particle physics or some kind of system, basically any kind of system where quantum mechanics plays a significant role. You might expect that you could get an advantage from simulating it quantum mechanically. But the idea, in this talk is really to think about quantum simulation not as a thing in itself for simulating quantum physics, but rather as a tool for designing algorithms for problems that might not have anything to do with quantum physics. So, you can think about adiabatic optimization, if you've heard of that, as a quantum mechanical process that you could simulate using Hamiltonian simulation in order to solve optimization problems. There are various kinds of quantum walk algorithms that get quantum speedups for certain kinds of problems, and you could implement those continuous time quantum walks using Hamiltonian simulation. And in this talk, and I think probably in some other talks in this in this meeting, we're going to focus on this idea of using Hamiltonian simulation to produce these quantum encodings of solutions of linear algebra problems. Okay, so the kind of workhorse of many of these algorithms, which is something that builds upon quantum simulation but sort of abstracts it into something that's useful for linear algebra, is this quantum linear systems algorithm. So in this quantum linear systems problem, we're given in the linear systems problem in general, we're given a system of linear equations and we would like to find the solution. So let's say we have a square system. We have, n equations and n unknowns. We want to find the solution of this matrix equation. So that's just A inverse applied to B, assuming that the matrix is invertible. But now if we want to solve this on a classical computer, or indeed even if we want to do it on a quantum computer, but our goal is to produce an explicit description of the solution, then we need linear time, time linear in the dimension of the system just to write down the answer. But, again, the idea here is going to be to change the model, think about a situation where our goal is just to prepare a quantum state proportional to the solution. And then under suitable additional conditions that say that we have the right kind of implicit specification of the problem. So we have some kind of ability to evolve according to A viewed as the Hamiltonian of a quantum system. So one way of doing that would be that it's a sparse matrix and we have appropriate black box access to its non-zero entries. And that we have the ability to efficiently prepare a quantum state proportional to the right-hand side of this system of equations, then we can efficiently prepare this state X. And so this was shown in an early paper of Harrow, Hasidim, and Lloyd from 2009 that sort of set off a lot of the work in this general area. Specifically, they showed that you could do this in time polynomial in the number of qubits it takes to represent the vector, so polynomial in the log of n, polynomial in the inverse of the error, and polynomial in the condition number, where the condition number is this quantity that somehow captures how close or far from singular the matrix is, because the problem should be really hard if the matrix is close to singular. So I'm not going to get into the details of how this subroutine works in this talk. Maybe we'll hear more about algorithms for this problem in other parts of this meeting. But the basic idea of the original algorithm was to use what's called quantum phase estimation to get spectral information about the matrix A through Hamiltonian simulation of some Hamiltonian dynamics related to A, and then somehow manually put in the inverse of the eigenvalue to get the desired state where somehow the eigenvalue has been replaced by 1 over the eigenvalue. So this was how the original algorithm worked, and actually there have been subsequent improvements that give faster algorithms. These improvements are not going to be so relevant for the applications that I'm going to talk about today, but just to mention that there have been some improvements that have shown how to get actually exponentially better dependence on the error and quadratically better dependence on the condition number. So the original algorithm had sort of kappa squared dependence on the condition number, but in fact it's possible to make it linear in kappa, and that's sort of the best you can do. Okay, but let me sort of move on and talk about the application of these ideas to differential equations, because that's the thing that we really want to focus on for this work. And let's start by thinking about the case of linear differential equations, because this was considered earlier, and well, this was considered quite some time ago, and it's a sort of it has some lessons to tell us about the nonlinear case. So let's imagine that now that we're given a linear ordinary differential equation, system of n equations, in n unknowns, and we have here, dx dt is some, linear function of x, some, I guess, affine function of x. So we can have some forcing term in general, and we have some, initial condition, and then our goal is to figure out what the solution is at some later time, right? So we're talking about the initial value problem. So quantum simulation is really just the special case of this, where the matrix A is anti-Hermitian and the system of equations is homogeneous. But you can consider the more general case, and in a nice paper of Dominic Berry in 2014, he showed how to do this for some more general linear ODEs using the quantum linear systems algorithm as a subroutine. And the basic idea is reasonably straightforward. So what you can do is you can approximate the dynamics of this system of differential equations through a system of linear equations using something like a finite difference approximation, where you sort of gradually evolve the system forward in time, and there's sort of linear conditions that tell you how the vector at some slightly later time should relate to the vector at an earlier time. And then, of course, there's some error that's introduced when you make that approximation, and sort of all the hard work and understanding the performance of this algorithm goes into carefully bounding that approximation error as a function of parameters of the system of equations, right? So you can do that by understanding what is the condition number of this linear system that you write down, but then you would like to describe that condition number in terms of sort of basic properties of the system of differential equations, and that's kind of the much of the technical work that goes into this paper is showing how to do that. Okay, so in this algorithm, of course, it comes with many of the caveats of the quantum linear systems algorithm. You need to have the right kind of implicit description of the linear system to be able to do this, of the system of linear differential equations, and also of the initial state. And you will only produce a quantum encoding of the solution, right? You produce this quantum state that encodes the solution, which is certainly not the same as producing an explicit description. And then you have to ask, what useful information can you extract from that? That's sort of a separate question that I'm not going to focus on here, but it is an important one for applications. There's an additional caveat that arises in the analysis of this algorithm that I want to mention, because it shows up again in the case of nonlinear differential equations, which is that it's important for the algorithm to be efficient that the norm of the solution does not decay exponentially in time. This is because, if you would have the ability to take a really small vector, one where the solution has decayed away exponentially, which is certainly something that can happen in general in the sort of evolution of, linear differential equations. If the solution decays away exponentially, and then you can somehow make a quantum state that, boosts that back up to norm one, right? You make the normalized quantum state proportional to that solution. Then, this ability allows you to post-select on exponentially small amplitudes, and that's something that's hard in general. In fact, it's sort of even harder than NP hard. It's harder for a kind of a bigger complexity class called probabilistic polynomial time. So that's something we don't expect to be able to do efficiently. And that means that there has to be some condition on the efficiency of the algorithm. This kind of thing is not happening. So that's just, it's just a necessary condition for the algorithm to succeed. It's just somehow inevitable that this is the case, because otherwise you would be doing something really computationally hard. So this initial work was really on these initial value problems and sort of, of a somewhat restricted form, but there's been a lot of later work to sort of generalize the idea of this algorithm to other situations, like where you have time-dependent coefficients or partial differential equations, or you look at boundary value problems. There's a variety of, different kinds of things that people have investigated. Okay, but what I want to focus on for this talk is the case of nonlinear differential equations. So what happens if instead of having a system of linear differential equations, the dynamics are really nonlinear? Okay, so actually this question was considered very soon after the original quantum linear systems algorithm of Haro-Hasidim and Lloyd came out, like maybe a month later or something like that. There was a paper on the archive by Layton and Osborne that considered this question, and they actually gave an algorithm for n-dimensional systems of nonlinear differential equations that had complexity polynomial on the log of n, which is exactly the kind of thing that we're sort of aiming for. So that sounds great. But the sort of problem with their algorithm is that while it has good complexity as a function of the dimension, it has a running time that's exponential in the amount of time that you want to evolve the system of equations for. And that's not so great because it means, you're really not going to be able to evolve for a very long times before the sort of, complexity of the algorithm is just too large for it to be useful. But so how does the algorithm work? Oh, there's a question. Yes. I think you're muted.
Okay.
There you go.
Just one question. So I just wanted to know if we would not have like a long-term memory, could we just make it iterative to like divide the exponential complexity to like blocks of like smaller time? So we know that could help, right? So for example, instead of having like 10,000 steps, we would have like hundreds of 100 steps. So can we do such a thing here? Or?
Right. So if I understand your question, I guess what you're sort of saying is that, like, well, if you know how to evolve for some amount of time without taking too many steps, why not just sort of break up the evolution into sort of segments and then use the output of one as the input to the next? Is that kind of the idea? Yeah. I mean, the algorithm actually kind of already has in some ways this division into steps, but this would not sort of save things for a reason that I'm actually just about to explain. Yeah, maybe let me go through like the rest of the slide and then let me know if it answers your question. So the main idea of their algorithm is to kind of use multiple copies of the solution to represent the nonlinearities, right? So this is a way that you can effectively have a nonlinear term. If you have like 2 copies of the solution, then a term which is quadratic in 1 copy of the solution is linear in 2 copies of the solution. So just by having multiple copies of the solution, you can somehow, get access to these nonlinearities. So that's exactly what they do. But the problem with this approach is that you use up these copies as you evolve. So, there's some process you have to go through that sort of turns, 2 states into 1 if you want to evolve the system forward in time by a little bit. And so, you have to have these multiple copies. So, one way of doing it is to have all the copies sort of around at the very beginning of, the algorithm, and sort of, make sure you have enough that you still have some left by the end of the algorithm. And actually, that's kind of the only thing you can do because of the no cloning theorem in quantum mechanics, which says that you can't sort of like take the state that you have after evolving for a while and then copy it. So you have these multiple copies that you can use to implement the nonlinear evolution. So, I think this sort of, hopefully this helps to answer the question. Like, I mean, this is basically what the problem would be. If you would evolve forward a little bit and you would have a copy of the solution, this is somehow not enough. You need to have multiple copies. And there would be some sort of like, tree that would grow exponentially into the past if you would sort of try to have them all ready at the outset of the algorithm. Yeah. So that's kind of the problem with that approach. And, you might think that perhaps there's no getting around it because actually nonlinear dynamics can do really computationally powerful things. So one place that this has been studied is in the context of understanding the computational power of nonlinear variants of quantum mechanics. And it's been shown, starting in some nice early work of Abrams and Lloyd, that if you would add nonlinear, I mean, quantum mechanics is linear, but if you would make up a variant of quantum mechanics that includes nonlinearities, then you could often use that to solve computationally hard problems, like NP-hard problems, or sort of like, even harder problems fast. So that's, I guess the way that I see that is it's an explanation maybe of why quantum mechanics is linear. But in any event, it means that if you believe quantum mechanics is linear, you shouldn't be able to efficiently solve those problems. And so maybe this is really just like a fundamental obstacle that somehow, it's just not possible to give efficient quantum algorithms for nonlinear dynamics. Right? And it turns out that I think it kind of is a fundamental obstacle if you want to like think about simulating nonlinear dynamics in general. But that doesn't mean that there aren't classes of nonlinear dynamics that you can efficiently solve. And so this is sort of what I want to tell you about, that we've, through this work, we kind of identified a subset of, all the possible nonlinear dynamics where we actually can give an efficient algorithm. And so by identifying some parameter that characterizes, whether we're in a regime where we can actually kind of keep things under control, we're able to give an efficient algorithm in some cases. Okay. So here is a, perhaps overly detailed description of the problem as we solve it. But kind of the main thing to focus on is this parameter R, which is this thing that really characterizes the sort of difficulty or tractability of the kind of instance of the system of nonlinear equations that we are considering. So let me sort of walk you through this. So just to keep things simple, we're going to focus on the case of quadratic nonlinearities. You could sort of generalize this, but this is what we focus on in our paper. And so here's a kind of a fairly general kind of quadratic system of differential equations. The nonlinearity here is represented in this way, where we think about it in terms of multiple copies of the solution, right? So this is a term which sort of takes a vector that's 2 copies of the solution and outputs something that's only, so this is like an n squared dimensional vector because it's U tensor U, but F2 is like an n squared by, is an n by n squared matrix. So it outputs an n component vector, right? So this is basically implementing a general kind of, quadratic function of the input. Then we have a linear term, and we also have an inhomogeneous term that we allow to be time dependent. We assume all the standard kind of stuff about the sort of access that we have to these matrices and to the initial state. So we have all the kind of sparse access that we would need to do the kind of quantum simulation and state preparation that we want to be able to do. So this parameter R is basically capturing like the strength of the dissipation, so the dissipative part of the linear dynamics, to the nonlinear and driving terms, right? So here, what it says here is that we assume that the eigenvalues of the linear part have real parts that are negative. So it's like a purely dissipative system. And this eigenvalue, lambda 1 is the one with the, least negative real part, right? So that's sort of like the weakest dissipation that you have in the sort of linear dissipation of the system. And so this parameter R is somehow characterizing, the strength of that dissipation relative to nonlinearities and driving. And so you can think about this as sort of being qualitatively similar to, although maybe not exactly the same as, the Reynolds number in the sort of nonlinear equations of fluid dynamics. But it's some, thing that we can apply to sort of like, or that we can use to characterize fairly general systems of nonlinear differential equations. Okay, so that's the sort of parameter that we're going to use to characterize the easiness or hardness of this, nonlinear differential, this quantum nonlinear differential equations problem. And so we have 2 main results that I want to, briefly tell you about for this problem. One is an algorithmic result that says that for some values of R, we can give an efficient algorithm. And the other is a lower bound result saying that for other, in another regime of R, we can prove that there is not an efficient algorithm. Okay. All right, so let's start with the algorithmic result. So what this result says is that if R is not too big, specifically if R is less than 1, then there's a quantum algorithm for this problem that has, polynomial query and gate complexity. Specifically, the complexity is only quadratic in the evolution time, right? So this is exponentially better than the result of Leighton and Osborne if we're in this regime where our algorithm applies.
Andrew, I think there's a question.
Yes.
Asked by Lexington. What if the solution blows up time t?
Yeah, right. So when you say blow up, you mean the norm is very large, I guess. So that's exactly captured by this parameter Q. So this parameter Q is exactly, going to infinity. Yeah. So that would be really bad. But if it were even finite but very large, that would be, that would be pretty bad. If it actually diverges, right, then this is going to be a situation where we can't give any, bound on the complexity of the algorithm. So that would be a.
I think you mean Q goes to 0, right? Because if U of t goes to infinity, then Q goes to 0.
Right. And so the comment in the chat, it says going to infinity. So I guess what they mean, the question means is that this would be going to infinity. So indeed, that would correspond to Q going to 0. Sorry.
Right.
No, I see. I'm confused. Right. So the thing which is a problem is if the solution, the norm of the solution would go to 0, and then Q would go to infinity. So in that case, we would have no bound. If this vector actually diverges, I think it can get sort of like arbitrarily large, and that's going to be okay. If it actually somehow goes to infinity at some time, though, this is some kind of I don't know, edge case that I would have to think about. Maybe that's somehow ruled out by some technical condition of our algorithm. I'm not absolutely sure about that. Yes, yeah, I understand now. You're talking about if this thing blows up. Yeah, I think it sort of can get, even very large, and this is okay. But yeah, I think, yeah. So as Nathan points out in the chat, indeed, the epsilon is an error in the is sort of a relative approximation error. So we only get a guarantee about the sort of quality of the relative approximation. That's true. But yeah, I think that sort of the norm of this thing could be arbitrarily large and we still have this guarantee, but I'm not sure what happens sort of like in some kind of pathological case where it actually diverges. I would have to go back and look at this.
Okay, yeah, we can certainly discuss this after the talk.
Yeah, maybe this is something we can save for discussion. But yeah, I mean, the situation that we're actually sort of more worried about is where this norm goes to zero, so that Q goes to infinity, because that's the situation where we have to worry about sort of post-selection, right? So if we would be able to post-select on exponentially small outcomes, we could use that to solve computationally hard problems. So the complexity of the algorithm should diverge in that case, and sort of you see that here, right? So, I mean, I should emphasize that, there are sort of non-trivial instances of this problem for which kind of this Q remains under control, and the sort of the running time of the algorithm is polynomial. So you can have this despite the fact that we're sort of requiring that there is dissipation, because of the fact that we have this driving term. So that's a point we could come back to again later as well if there's interest in sort of this regime where Q gets small. Okay, great. But let me just talk, briefly about what some of the elements are that go into this analysis. So basically, the first thing we do is try to get this into the regime of sort of linear systems of equations. And so there's a kind of a linearization procedure, which maybe some of you are familiar with, called Carleman linearization, which we can use to sort of capture the nonlinear dynamics of this n-dimensional system through the linear dynamics of a larger system of equations. And I'll explain a little bit on the next slide how that works. But that's actually like a well-known technique for dealing with nonlinear systems of equations. We give some sort of new convergence analysis of that technique that's appropriate to our situation. But that's the basic idea of this linearization procedure is quite old. And then from that point, we just apply the kind of, now we have a system of linear differential equations. So we just apply the standard kinds of ideas. We discretize in time, and then we just have to work out sort of, just have to do the complexity analysis in terms of the procedure for preparing the initial state, and sort of how the performance of the quantum linear systems algorithm depends on parameters of the system of nonlinear equations, like, for example, this parameter R. Okay, so let me briefly explain the idea of this Carleman linearization procedure. So the idea is that we can approximate the system of nonlinear differential equations by an infinite sequence of linear differential equations, where the variables in that larger system are tensor powers of the vector, right? And so let's see how that works. So let's think about the simple special case where we just have a scalar equation, so we don't have to write any tensor products. And then the kind of general quadratic nonlinear differential equation looks like, du dt is this just quadratic function of u. And so now the idea is, this is definitely like not a linear system, system of differential equations. But if we would sort of think of u squared as an independent variable in its own right, then this expression would be linear in u and u squared. Now, to actually think about that as a larger system of differential equations, we would need a dynamical equation for u squared. But we can get that just using basic calculus, right? I mean, the time derivative of u squared is just by the chain rule 2 times u times du dt. And we have an equation for du dt, so we can plug that in and we get this expression, which is now an expression in u, which is linear in u, and it's linear in u squared, right? I mean, if we're thinking of u squared as its own variable, but now we have this u cubed term. So now we have to do something about that, because that's not linear in u or u squared. It's either, cubic in u, or, quadratic in u and u squared, or, something like that. But you see that we can just do the same thing again. Now we can call u cubed its own variable, and we can get a dynamical equation for it, using the chain rule, et cetera. Now, this process will never terminate, right? We'll just get an infinite system of equations. But one thing we could do is we could say, suppose we chop it off at some point. Can we show that we get a good approximation by doing that under certain conditions? And it turns out that you can do that. So here's sort of what the system would look like in general if we have not just scalar equations, but we have vector equations, and we get some kind of larger matrix as a function of the matrices F0, F1, and F2 that characterize the nonlinear system. And then what we want to do is we want to show that, if we truncate this at some high enough levels, you hear this has been truncated at level capital N, that will give us a good approximation. I think there was just a hand up. Does somebody want to ask a question? No. Okay. So, and so we were able to show a kind of a convergence theorem that shows this, that specifically if you take a capital N that's like, proportional to like, here's how it depends on various parameters, but in particular, it only has to grow logarithmically in the total amount of time you want to evolve the system for, then this will give you an approximation of the solution to within, some desired amount delta. So that's kind of how that's kind of the main sort of new technical thing that's going on in this algorithm, relative to other algorithms for linear differential equations. Okay, so having talked about the algorithm, let me briefly talk about the idea of the lower bound. Yeah, Lynn.
Doesn't this depend on some other parameters like R and the U of t and things like that? So that's the
that's right. So here I've described the sort of explicit dependence in terms of like the strength of the nonlinear term. This is kind of, this is not a sort of full technical description of the lemma. Ultimately there will be some dependence on R of the analysis. And it's going to be necessary for R to be, not too large for this procedure to converge well.
Okay. Yeah. Thanks.
Okay, great. And in fact, we're going to see that in the sort of effectively through the next thing that I wanted to mention, which is this lower bound result. So as I mentioned before, we already know that nonlinear dynamics in general can be computationally, powerful because of, so nonlinear quantum mechanics in particular can be used to quickly solve hard computational problems. But that's not a case with dissipation, right? In nonlinear quantum mechanics, the state vector always remains normalized, even though it's evolving in some nonlinear way. But we really want to sort of see that this problem still remains hard, even under this condition that there's some dissipation, as long as the dissipation is not too strong. And so what we're able to show is exactly that, namely, in particular, if this parameter R is at least the square root of 2, so we don't know if it's like 1.01, what exactly the situation is, but if it's at least the square root of 2, then you can construct an instance of this problem as we describe it, so that if you could give an algorithm that would always work for any instance of that problem to produce the quantum state, that represents the output of that, approximately represents the output of that system, then you would have to do that in using a quantum circuit of exponential size. The complexity of doing that is going to be is definitely going to be exponential in capital T in general. And the way that we're able to show this is actually quite similar to the way you can show the hardness of nonlinear quantum mechanics, specifically because you can use nonlinear dynamics to rapidly distinguish non-orthogonal states, right? So we know that in quantum mechanics, it should be very hard to distinguish quantum states that are very close to each other. And you can give a, you can show that a quadratic ordinary differential equation, at least as long as R is big enough, that it can be used to rapidly distinguish non-orthogonal states. And so like, here's maybe I won't go through the details, but here's a sort of an example of how using some simple nonlinear dynamics, using a value of R that's, let's say, the square root of 2, you can have sort of trajectories that exponentially diverge from each other. And thus, in a sort of a short amount of time, you can distinguish these, quantum states that should be hard to distinguish. Okay, so those are sort of the main results. So maybe I should sort of summarize the main things that we've seen and just talk very briefly about some open questions. So in this work we've shown how to efficiently produce a quantum state that encodes the solution of a system of nonlinear differential equations in a certain regime, right? In this regime where this parameter R is not too large. And under some other technical conditions, the one that sort of, I think is the most significant is that it's important that the solution does not decay exponentially, right? So if the solution would decay away exponentially and you would try to produce a, normalized version of that, that's a computationally hard thing in general. But if you consider a system of nonlinear differential equations in which that does not happen, and R is less than 1, then that's something that you can do efficiently on a quantum computer. Yeah, there's a question.
Biswaji, can you unmute yourself? I think I just unmuted. Asked you to unmute. No? There's
maybe
chat. Yeah, go ahead.
Maybe I'll just continue. Yeah. Okay. So, right. So, we know that this problem is sort of the sort of general class of problems that we're considering here is, BQP complete. I mean, it includes sort of as a special case, the sort of limit of linear differential equations. And even in that case, this problem is as hard as anything a quantum computer can do. So the general class of things that we're able to handle definitely include, things that we think are classically hard. But I think it's, interesting to ask, about applications where we can potentially really take advantage of the nonlinear dynamics to do something that goes beyond what we can do in the linear case. As I mentioned, this limitation that we not have exponential decay is really sort of fundamental. That's a condition that has to be there. This is something that, does not rule out the possibility of having sort of interesting nonlinear dynamics because, even though we require dissipation, which somehow forces the state vector to decay in general, we have this possibility of including a driving term. And so because of that, the solution does not have to decay. The solution does not have to decay away exponentially. The forcing term can kind of, keep it alive and still be in this regime where, R is less than 1, but nevertheless, this parameter Q is not exponentially large. Still that being said, there are, these technical conditions that have to be satisfied. So it's not like we could just apply this to any system of nonlinear differential equations and get something efficient. So you do have to be a little bit careful about finding, regimes where it's interesting to apply this algorithm. We also have this kind of hardness result. And I didn't have a chance to mention it, but we have some, to show you the details, but we have some numerical evidence suggesting that, while the algorithm can't be efficient in general for larger values of R, there can be special cases where even though R is much larger than 1, nevertheless, the algorithm can be efficient. The sort of Carleman procedure can, give a good description with sort of like fairly low truncation. So I think it would be interesting to understand better, when that happens and when, this sort of limitation does not really apply. Okay, so let me just quickly conclude. So, I think there's a bunch of interesting questions to think about related to this kind of algorithm. There's a bunch of sort of technical questions about, sort of intermediate values of R and the precise dependence on T and epsilon. But I think the kind of thing that would be the most interesting to explore is when you might be able to apply these kinds of ideas to, handle interesting applications. In this work, we've really focused on developing an algorithmic tool that under some kind of technical conditions would let you get some kind of handle on solutions of systems of nonlinear differential equations. But I think it'd be great to understand better how you can actually apply this. And this issue of sort of identifying conditions under which maybe it would work even for larger values of R, even for weaker amounts of dissipation, that's one thing that maybe could be helpful in identifying those applications. But in general, I think thinking about how you could use these kinds of algorithms for various kinds of scientific computing applications or anything would be really interesting to think about. Okay, so I think I will stop there and I'm happy to take more questions.